Next, that is the spline development. Okay, so first order splines find straight line equations between each pair of points. That is, go through the points. See here. See, like that. Okay, this is the first order spline. So straight line equation between each pair of the points. So these are two pairs. First one, second one is the straight line. 2, 3 straight line. 3, 4 straight line. So the first straight line equation between each pair of points is the first order spline. So first order spline means straight line. Next, second order spline. There is a find quadratic equation between each pair of points. Go to the points, match first derivatives in the interior point. So it is the interior points. These are the points of the second order. Okay. So splines find the quadratic equations. Okay, quadratic. That is an x1 equal to 2. So the order is 2. Then match first derivation of the interior points. What are the interior points of the first one? That will be matched into the lines. This is the line of the first order. Third order splines find cubic equations between each pair of points. This is the equation in the cubic spline. This is the interpolating cube. So go through the points, match first second derivatives at the interior points. Okay, so what are the interior points that are match of the particular lines? Okay, the result of the cubic spline interpolation are different from the results of an interpolating cubics. Next, cubic splines. While data of a particular size presents many options for the order of spline functions, cubic splines are preferred because they provide the simplest representation that exhibit the desired appearance of the smoothness. So linear splines have discontinuous first derivatives, quadratic splines have discontinuous second derivatives and require setting the second derivative at some point of a determined value. So quadratic or higher order splines tend to exhibit the instabilities inherent in higher order of the polynomials. Next, in general, the ith spline function for a cubic spline can be written as Si of x equal to ai plus bi of x minus xi plus ci of x minus xi whole square plus di of x minus xi whole cube. For n data points, there are n minus 1 intervals and thus 4 of n minus 1 unknowns to evaluate to solve all the spline functions to the coefficients. Given a set of control points, cubic interpolation splines are obtained by fitting the input points with a piecewise cubic polynomial curve that passes through every control point. Suppose we have n plus 1 control points with coordinates pk equal to xk, yk, zk, where k equal to 0 to n. That is p0, p1, p2, p3, p3, pk, pn. Okay, so likewise we have to draw. Okay, so we have the n plus 1 control points with the coordinates of pk, xk, yk, zk, k equal to 0 to n. We can describe the parametric cubic polynomial that is to fit between each pair of control points with the following set of equations: ax uq plus bx u square plus cx u plus dx, y of u ay uq plus by u square plus cy u plus dy, z of u az uq plus bz u square plus cz u plus dz. In Hermite form, let's look at an alternative way to describe the cubic curve. Instead of defining it with the 4 control points as a Bezier curve, we will define it with a position and a tangent at both the start and end of the curve P0, P1, V0, V1. See, this is the Hermite curve. So this is the Hermite curves. Okay, so P0, V0, P1, V1. Okay. So we want to the value of the curve at t equal to 0 to be x of 0 equal to p0, and at t equal to 1 we want x of 1 equal to p1. So we want the derivative of the curve at t equal to 0 to be v0 and v1 at t equal to 1. The x of 0 equal to p0 equal to a0 cube plus b0 square plus c0 plus d equal to d. X of 1 equal to p1 equal to a1 cube plus b1 square plus c1 plus d equal to a plus b plus c plus d. X dash of 0 v0 equal to 3a0 square plus 2b0 plus c equal to c. X dash of 1 equal to v1 equal to 3a1 square plus 2b1 plus c equal to 3a plus 2b plus c. So Harmonic curves P naught equal to D, P1 equal to A plus B plus C plus D, V naught equal to C, V1 equal to 3A plus 2B plus C. Next, Hermetic curves P naught equal to D, P1 equal to A plus B plus C plus D, V naught equal to C, V1 equal to 3A plus 2B plus C. See here, P naught, P1, V naught, V1 equal to 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 1, 0, 3, 2, 1, 0, A, B, C, D. Okay, the matrix form of Hermetic curve A, B, C, D equal to 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 0, 3, 2, 1, 0 power inverse P0, P1, V0, V1. Okay. Next, A, B, C, D equal to 2, minus 2, 1, 1, minus 3, 3, minus 2, minus 1, 0, 0, 1, 0, 1, 0, 0, 0. So P0, P1, V0, V1. Okay, that is the matrix form of the Hermite curve. This is the matrix form of Hermite curve. Okay. Next, x equal to t cube t square t 1 into 2 minus 2 1 1 minus 3 3 minus 2 minus 1 0 0 1 0 1 0 0 0 p0x p0y p0z p1x p1y p1z v0x v0y v0z v1x v1y v1z. So x equal to t into bhrm, that is a Hermetic curve dot ghrm, that equal to x equal to t dot c. The Hermite curve is another geometric way of defining the cubic curve. Okay, it is the another way of the defining the geometric curves. Okay, so we see that ultimately it is another way of generating cubic coefficients, that is cubic coefficients. Okay, we can also see that we can convert a Bezier form to a Hermite form with the following relationship, that is C into Bz into Gbz equal to Bhrm dot Ghrms. Okay. So the degree of Bezier curve is determined by the number of control points. So example, Bezier curve degree equal to 1 1, difficult to blend the neck toward the line segment P4 P5. Of course we can add more controllers points, but this will increase the degree of the curve, that is the increase of the computation of burden. See here, this is likewise 0 1 2 3 4 5 6 7 8 9 10 11. Based upon that we can draw this one. See, likewise. Okay, so the degree of Bezier curve is determined by the number of control points. Okay, it will be increase the computation of the particular splines. See next, join many Bezier curves of lower degree together. There is right figures. This is one. This is so, but maintaining continuity in the derivatives of the desired order at the connection point is not easy or may be tedious and undesirables. Okay. See, moving a control point affects the shape of the entire curve. That is global modification property, that is undesirable. Thus, the solution is B-spline. The degree of the curve is independent of the number of control points. Right figure, B-spline curve, degree 3 defined by 8 control points. Okay. This is the curve. See, this is the curve. So these are the points. Based upon the points, you can draw the curve. This 1 and 4 and 5 and 6 and 7. Okay. Thus the solution is B-spline. See. Next, in fact, there are 5 Bezier curve segments of degree 3. That is 1, 2, 3, 4, 5. Okay. To the together to form the B-spline curve defined by the control points. So little dots are subdivided the B-spline curve into Bezier curve segments. See here. These lines 1, 2, 3, 4, 5. So little dots. These are the little dots. So these are the little dots. See, these are little dots. So little dots subdivide the B-spline curve into Bezier curve segments. Subdividing the curve directly is difficult to do. So subdivide the domain of the curve by points is called knots. These are called as the knots. N-O-T-S. Okay. Next. In summary, to design B-spline curve, we need a set of control points. So mainly it will depend upon the control points. So based upon that control points, we can draw the curves, splines, whatever may be. So what is the main difference of the Bezier curve and spline? Okay. So the control points is set of knots and of a degree of the curve. See knot. Each subinterval endpoint, there is a knot and knot vectors of the B-spline. Knot. Each subinterval endpoints UI. That is knot vector. Entire set of selected subinterval endpoints. Next, choose any values for subinterval endpoints. Only condition UI less than equal to UI plus 1. U min and U max depend on the number of control points we select of n value for d, that is a degree. So P of u equal to sigma n I comma k of n u p I, that is u0 less than u less than um, that is 1.0, where the basis function n I comma k of u, degree of curve to k minus 1, control points pi to 0 less than I less than n, not u to u not less than u less than m equal to n plus k. See, P of u equal to sigma n I comma k of u pi, that is u naught less than um, ui to naught, then ui comma ui plus 1 to naught span. Okay, ui comma u2 and so on um to naught vector. These are all called the vectors. Ui is the naught, ui comma I plus 1 is the span, u0 to um is for naught vectors. Okay, so the point on the curve that corresponds to a knot ui2 knot point comma p of ui, if knots are equally spaced to uniform of 0 comma 0.2 comma 0.6 comma 0.8 and so on. Otherwise there is a non-uniform 0 comma 0.1 comma 3 comma 4 comma 0.8 and so on. See, uniform knot vector, individual knot value is evenly spaced, that is 0 comma 1 comma 2 comma 3 comma 4. Then normalize it to the range of 0 comma 1, that is 0 comma 0.25 comma 0.5 comma 0.75 comma 1.0. Next, see, types of B-spline uniform knot vector, that is non-periodic knots, that is the open knots, periodic knot, that is non-open knots. See, in non-periodic knots, first and last knots are duplicated k time, that is 0, 0, 0, 1, 2, 2, 2. Curve pass through the first and last control points. Next, in the periodic knots, first and last knot are the duplicates, same contribution. 0, 1, 2, 3. But here we can define the some duplicates. Okay. Curve does not pass through endpoints, but the non-periodic, the curves are passes through the endpoint, last endpoint, but the periodic knots does not pass through the endpoints. And the periodic knots used to generate closure curves when first equal to last control points. See, these are the non-periodic curves. See, these are non-periodic curves. These are the periodic knots, not from the ending. See here, starting ending ఉండదండి. Okay, this is the closed knots, completely will be closed. Okay, so these are the types of the B-splines. That is the non-periodic knots, and next one is the periodic knots. See, equation n I k of u equal to u minus ui n I k minus 1 u by ui plus k minus 1 minus ui plus ui plus k minus u n I plus 1 k minus 1 of u ui plus k minus u I plus 1 n I 1 equal to 1 0 ui less than or equal to u less than or equal to ui plus 1 0 otherwise. In equation 1 1, the denominators can have a value of 0 in prism to the 0 if the degree is 0 basis function n I 1 of u is 1 if u is the ith knot span ui ui plus 1. For example, we have take 4 knots u not equal to 0, u1 equal to 1, u2 equal to 2, u3 equal to 3. Knot spans 0 1 2 on 0, 1, 1, 2, 2, 3. So the basis function of the degree is 0 or n 0, 1 of u equal to 1 on 0, 1 and 0 elsewhere, n1, 1 of u equal to 1 on 1, 2 and 0 elsewhere, and n2, 1 of u equal to 1 on 2, 3 and 0 elsewhere. This is shown in the figure. See here. 1 basis on 1, 2 basis on 2, 3. So likewise we can draw the spline basic functions. Okay, see, degree 0 and 0 1 u of 1 n2 1 2 3 and zeros. Okay, so likewise we can draw the splines. See, properties. The m degree b spline function are piecewise polynomial of degree m2 have c power m minus 1 continuity, that is b spline degree 3 have c square continuity. So in general, the lower the degree, the closer a b spline curve polynomial control polynomial degree 7, degree 5 and degree 3. So equality m equal to n plus k must be satisfied number of knots equal to m plus 1. K cannot exceed the number of control points n plus 1. Each curve segment is affected by k control points as shown by past example is a k equal to 3, p of equal to n I minus 1 comma k, p I minus 1 plus n I comma k p I plus n I plus 1 comma k p I plus 1. So local modification scheme changing the position of control point pi only affect the curve c of u on the interval ui comma ui plus k. So this is the example. Modify the p2. Okay, this is the modify of the particular p2 values. Okay, control point p2. Strong convex cell property, that is a b-spline curve is contained in the convex cell of its control polynomial. This is the window. This is the window. Okay. More specifically, if u is the knot span ui comma ui plus 1, then c of u is in the convex hull of control points p I minus p comma p I minus p plus 1 comma p I. So degree equal to 3, k equal to 4. Convex hull based on the 4 control points. So this is the based on the contour. This is a windows like that. So non-periodic B-spline curve C of U passes through the two end control points of P0 and Pn. Each B-spline function n k comma m of t is non-negative for every t, and the family of such functions sum to the unity, that is sigma ni comma k of u equal to 1, I equal 0 to n. Applying invariance to transform a B-spline curve, we simply transform each control points. So Bezier curves are special cases of B-spline curves. So varies of dimension, a B-spline curve does not pass through any line more times than does it control the polyline. It will not be passed through more times. Okay, so it does not pass through any line more times than the passes. Okay, so these are the 8 properties. Edge B-spline function are precise polynomial degree 3. Lower degree close a B-spline curve. Its control polynomials m equal to n plus k, that the not equal to m plus 1. So each curve segment affected by k control points as shown by the past examples. Then local modification scheme, we have performed the local modification schemes. Strong convection property will apply to the particular spline curve. Non-periodic B-spline curve, that is passes through the two end control points. Variation dimension, spline curve does not pass through any line more times of the does it control the particular polynomials. Okay, these are the 8 properties based upon the these are the 8 properties. Based upon these 8 properties, we can draw the curves using of these splines, B splines. Okay, so Bezier curve and splines are the most important of the. You can draw the smooth curves on the particular lines. Okay, curves and lines. Okay, thank you. So this is the most important, the fourth unit, that is the Bezier curve and splines. Okay, so already we discussed the problems on the classroom. Okay, thank you.